Hello class, I'm just going to go through how to do some different problems. So this is probably going to be in class on Thursday, if I remember my lessons right, but right before now you should have just gotten this packet that says another angle on F equals MA at the top. Seems like a big packet, but we're not going to do a whole lot of it, and I'm going to do portions of it from you as well. So make sure you have this packet out. Again, starts on page 1, goes through page 10, but we're not going to do all of that. So if you don't have that out, have the teacher pause the video and get that out really quick, because I'm going to give you some problems to do on here, and I'm probably going to do about half of them with you. Teacher probably already put this on the board, but these are the problems that I want you to do out of this packet. Sorry about that. There you go. So out of this packet, page 3, 6 through 7. Page 5, 1 through 4, page 6, numbers 5 and 6, page 7, 1 through 3, page 8, 4 through 6. Pause the video if you need to get all of that down, but again, probably about half of that I'm going to do for you right now. But in total, this is what we're going to do. Okay, so once you have those numbers down, jump over to page 3 on your packet. So here we are on page 3. I already have portions of it kind of written in there. And I'm sure this video isn't going to show up very well, showing the text on these pages. So make sure you're kind of listening to what I'm saying as well. So just on page 3, number 6 and 7, do these on your own. But number 5 here, I'm going to kind of do that for you, I guess even though that wasn't on the list. But when vectors are added using the head-to-tail method, the sum is known as the resultant. We've talked about that before. We know what resultant means. When force vectors are added, that sum, or resultant, is also called the net force. Okay, we learned about net force, we learned about resultants, but we never called one thing the other. Okay, so when you add force vectors together, that is a resultant, but that resultant is the net force. Those names literally mean the same thing. Just 6 and 7, answer those really quick on your own. I guess I'll go ahead and kind of do number 6 with you here as well. Several forces act on object. The vector sum of these forces ends up being 0 newtons. The object is described as being what? Anytime the net forces are 0, we know the object's not accelerating, and we know it's at equilibrium. So answer B on option 6. Okay, so simple one. Just make sure that we know that's a term. That's something that might kind of pop up a little bit later as the year goes along. But that is exactly what having a net force of 0 means. You're at equilibrium. Then do number 7 on your own. Then we jump over to page 5. So here we are at the bottom of page 5. And I give you all 4 on there. Now I'm going to do some of these with you here. So let's just look at this first one. It says, for following situations, draw and label the force components as the projection onto the axes. So really simple. All you're doing here is on number 1. So this is one of the ones I said to do. I'm going to do it for you. We're pulling with a force of 75 newtons along here. If you can see my writing there, 75 newtons at an angle of 45 degrees. All you have to do, find the x and y components. X components we always find by doing the vector times cosine of the angle. So to find that, it was just 75 cosine 53. That's how we always do x components. Y components are always equal to 75 sine of 45. 45 angle, they're going to be both the same. Punch that in your calculator, you get 53. So x and y components, same thing we've been doing for chapters, but now it's with forces. On your own, do number 1B. Then jumping on down to number 2 here, kind of a pick all that applied type question. Give you a second to shift your paper down to number 2. And again, tell Mr. Levitt to pause the video at all if you need to, if I'm talking too fast. Which of the following is always true of an object in equilibrium? B through F. So B, C, D, E, and F are all the ones that would apply there. B, object is maintaining its state of motion. That means it's not speeding up, slowing down, or changing direction. So that would be true. Velocity is not changing. Absolutely true. Net force on the object is 0 newtons. That is what equilibrium means. E, the object is not accelerating. Also true. That means the same thing as this, as letter C. And F, the individual forces acting on the object are balanced. So all of those would be true. A and G would not be true. The object does not have to be at rest. And on G, all of the individual forces do not have to be all equal in magnitude. That could happen, but would be a more rare instance. You don't have to have every individual force all be equal to every other individual force. So do number 3 on your own. Number 4, I want you to look at, I'm not going to explain a whole lot, but it's referring to this picture here. I'm going to go ahead and give you the answers. But in this, F1x is equal to F2x. These two forces, this object's at equilibrium. That means they only have 2 horizontal forces. The 2 horizontal forces that we see up here add up to 0, so they're equal. F1y, we can just look at the picture. This, as compared to F3, those aren't equal. This is way smaller than that. Same for F2y. F2y is way smaller than that force as well. Then this last one, F1y plus F2y, has to be equal to F3. So this is like the sine problem, kind of that we talked about the other day, except for our angles are going to be different here. But long story short, this y component and this y component are teaming up to cancel out this guy. Okay? So we have 2 vertical components, say from a string or something, that are pulling upward, that are keeping the object in equilibrium from, say, if this was the force of gravity, from keeping that object down. If you were to write that out in an equation, say the net force in the x is 0. We know that because the object's in equilibrium. If they didn't say that in the problem, they should. It's kind of implied in the problem, but it doesn't look like they exactly say that. I think they want you more to look at the picture. But all of the horizontal forces have to cancel out, and all of the vertical forces have to cancel out. We're used to there just being 2 vertical forces, but in this case there are 3. So F2y and F1y are both upward. Those together are canceling out F3. And so it's a lot like that sine problem that you guys saw on the video yesterday. So there's number 4 for you. So all you guys need to do is 1B and number 3 on that page. We move along to page 6. Okay, here's some more sine problems. So kind of a revisit from what we did on the videos yesterday, where you have 3 different problems here. A sign, or a painting that's being hung from 2 strings at 15 degrees, one at 45 degrees, and one at 60 degrees. And it's really the same thing as the identical problem we did on the video from the other day. Since these angles are equal, that means that the tensions have to be equal. But what we're going to wind up seeing is that the tension is greater when we're at a low angle than when we're at a high angle. So if we look at just the first example here of the sign at 15 degrees, the weight of the sign, it says, is 10 newtons. So there's 10 newtons. That means each of these strings, vertical components, is supporting 5 newtons. So the vertical component there is supporting 5 newtons. And from that, we get this picture. They give you this on the page. The vertical component is 5 newtons. You know the angle is 15. So you can just use trigonometry using sine. I have it kind of written up here. I'm not going to, spell the whole thing out for you. But once you do the trigonometry there, you realize that the hypotenuse here is 19.3 newtons. The tension is higher than the weight of the sign, which might be a little bit surprising as well. Okay, so 19.3 newtons is the hypotenuse. And that means that each of these wires are going to have a force of 19.3 newtons in them. Go on to do the 45-degree example. Same type of deal. You wind up with this picture. The vertical component of one of the wires is supporting half of the weight of the painting. You've got a 45-degree angle. Use your opposite side, your angle, to find the hypotenuse. And you wind up realizing that the tension in the wire is 7.1 newtons. Still higher than half of the weight of the sine, but definitely a lot less than 19.3. So I did those first two for you. Go ahead and do the third one. It's basically just a repeat of the first two problems. Number 6 on that same page. So we're number 6, page 6 right now. Same kind of deal, same kind of thing as the sine problem we did from the other day. Here we have a 1 kilogram book hanging down, supported by two strings that are each at an angle of 1 degree. That's a really low angle. That really low angle is going to mean the tension is going to wind up being pretty high. So that means that the vertical component of each of these two forces is supporting exactly half of the object's weight. So the vertical component here is 4.9, like we see here, 4.9. A measly little 1 degree, so you've got the angle, a side. So again, we can use SOHCAHTOA angle. This is the opposite side. We want the hypotenuse. The hypotenuse is F2 or F1 here. They're only equal because the angle is the same on both sides. Do your trig, and you wind up realizing that your answer is a very large 281 newtons. And this is just a good example to know that there's always got to be slack in a line that's supporting something. Think of a high tension cable, like the power lines running down the road, or a giant rope that's going from a tugboat to some huge tanker ship. There always has to be slack in it, like you see here. Why? Because a horizontal force cannot apply a vertical force. In order to support this weight, you need a vertical force. This string has to have some vertical component to it. If this line was horizontal string can't be pulling up on anything. So that's what creates that slack. And in a really thick, tug rope from a towboat to a giant tanker ship, even though there's, hundreds of thousands of newtons of force in that line, there's always going to still be sag in it. Why? Because that thing's so thick that it has to support its own weight. It can only do that, when, let me just drop more horizontal here. It can only support its own weight when it is, kind of has some slack in it. And you think, how is it pulling anything when it has that slack in it? Because its own weight needs to be supported. In other words, a horizontal force cannot apply cannot hold something vertically. So any line that's supporting something, that's holding something up, needs to be at least a little bit vertical. Okay, a few more here. So we're going to jump over to page 7. We just say 1 through 3. I'm going to do about half of this with you. So if you look at number 1 on page 7, I'm going to do the first one on 1 and the first one on 2. And you guys are going to have to do these two kind of on your own. So the first one here, we see some forces acting on an object. This is like problems we've done before. Determine the acceleration value for the following two objects. Normal force and weight are canceling out, so there's no vertical net force, but you have an applied force. Your applied force, since that's the only force that doesn't cancel out, that's your net force. And then we want to know the acceleration. The acceleration is equal to net force over mass. That's Newton's second law. It's a simple problem. Net force is 12, mass is 2, your acceleration is 6 meters per second squared. Real simple. It's going to wind up being a similar thing over here, but you have friction in opposition to your applied force. So your net force is going to be a little bit more when you add friction into the mix. So see if you can figure that one out. We should anticipate the acceleration being less than 6. That's how one way you can kind of check your answer there. Number 2, okay? This is another one where we're just finding the components. Sorry, line this up a little bit better for you here. 13 newtons at an angle of 23 degrees. Find its vertical component and its horizontal component. Hopefully you remember how to do that. The force times cosine of the angle. This is the force times sine of the angle. Have that written right there. So, not going to spend much more time on that because that's essentially the same thing as problems we've done before. So, you would go ahead and do on your own, do number 2 on this same page. here and here. And again, should not be a long problem. All right, the first one on number 3 is a little bit more involved. So the weight of the object is pulling down. We have an applied force pulling the object kind of up in this direction at an angle of 23 degrees. So a force at an angle. So this is going to, the fact that this force is at an angle is going to change some things. Okay, so your normal force is not just going to be equal to your weight anymore. Now, why is that the case? So let me draw this problem out a little bit better so you can see it, since this is a harder problem. So if you have your object, okay, here's your object, and I'm just redrawing what they gave you on the problem. They said Fg is 19.6 newtons. There's some normal force acting up. We need to know what that is. And we have an applied force that's pulling at 23 degrees above the horizontal. That applied force is 13 newtons. So that's information they gave you on number 3 on page 7. Now, the objective is to figure out all the other blanks that they have there. Okay? Figure out what Fx is, what Fy is. What the normal force is, the acceleration, as well as the net force. So, first let's figure out what the acceleration is, and then let's figure out what the net force, what the normal force is, because it's going to be a little bit different this time. This problem's actually a little easier because there's no friction. Once there's friction, it gets a little bit harder. Okay, so first to solve for the acceleration, we want to know what that is, right? And first we have to know what the net force is. Let's draw that like that so we don't get confused. Net force is equal to something. Okay, so we have to find the first before we can find it. Now, in the earlier problems, you already figured out what the x and y components of Fa are, what your applied force is, It was 12 newtons, and this was 5.1 newtons. We did that on the earlier part of the page, with the same, like the first one on number 2. So, in this problem, we're only exerting horizontally. Okay, they're kind of giving you a problem. But if you don't see that just now, just think as kind of resting on the ground. We're not accelerating up or down, say anything about it. So all the vertical forces are still cancel out. So all I have to worry about is horizontal forces. Okay, in vertical, normal force, the force of gravity, and the y component of applied force all cancel out. I like to think as the vertical component of your applied force and normal force are teaming up to cancel out this. We'll come back to that. For our purpose now, there is no friction, but our horizontal force is 12 newtons. This is the force that doesn't cancel out. So, quite simply, that force is 12 newtons. Like it was on the problem and find the equation, know that it is equal to mass. So, 2 because so to times g equal to mass
same page. Okay, so here's all the answers to the first part of 3. For the second part of 3, it's the same kind of problem, but now there's friction. Okay? And since there's friction, that means that the normal force is affecting the amount of friction. So really most components here are going to wind up being the same as the previous problem. Except for that there's a force of friction that's going to affect your net force, which is going to affect your acceleration. But since your applied force is the same, your normal force is actually going to be the same. So really this one should be pretty simple for you, because other than the net force being different, which in turn your acceleration would be different, everything else is going to wind up being the same in the previous problem. Your normal force, your Fy, and your Fx, since we have the same applied force. Okay? So that one's really not too much of a departure. On to the last few now. So on number 4 here, it talks about a problem which they're arguing about how much the normal force is going to be. Object sliding across the ground, gravity is 100 newtons going down, and you again have an applied force at an angle. Once you find the y component of that force, it winds up being 25 newtons. And so this question just asks, like, well, 3 people are debating what the normal force is going to be. One person said it's going to be 50, one person says it's going to be 75, one person says it's going to be 100. The right answer to that is that it's 75. Why? Now, if there was no applied force, it would just be 100. But this applied force is helping pull up a little bit. It's relieving some of the force that the normal force has to apply. So since this is 25, this is upward and positive, this is upward and positive, you need those two things to add up to a positive 100 to cancel out the negative 100 Newton force of gravity. Okay, so that was kind of more of a concept question. But again, you're seeing that idea of now that you have an applied force at an angle, it's changing what the normal force is. And since you're changing what the normal force is, you're changing what the friction is. Now, on the one on the previous page, they told you what the friction was, so it didn't really change what you do a whole lot. But looking at number 5 here on the same page, sorry. Number 5 here on the same page, I kind of did it for you. But here, they want you to know, they want you to figure out how much the force of friction is. You figure out the force of friction using the friction equation, mu k Fn. But you first have to figure out the normal force, much like how we figured it out what it was up here. The normal force is not equal to the weight anymore. This is a harder type of problem. So I did most of the work for you here. The vertical and horizontal components of the applied force, find those first. If you can't see what this says, it's 18.4 and 33.2. It gives you the mass, so you know what the weight is. Just this number times 9.8 is going to be this number. The net force is going to be found by taking the friction in that direction to the left. That's going to be the vector sum of friction to the left and the horizontal component of the applied force to the right. But we don't know what this is yet. Okay, so we have to figure out what this is first, and then figure out what the net force is, and figure out what the acceleration is. So once you do that, okay, so we have to first actually determine what the normal force is. Okay, so that's our blank that we have filled in here. So we find the force of gravity by multiplying the mass times 9.8. That's 29.4. So you have 29.4 going down. You also have the vertical component of the applied force here. Just 38 sine of 29. That's 18.4. So you have 18.4 going upward. But 18.4 going upward isn't going to cancel out 29.4 going downward. So how much more upward force do we need? When you do the math there, you need 11 more newtons. This blank plus 18.4 is equal to 29.4 in the opposite direction. So that means that our normal force is 11. Normal force is 11 newtons. Now that I have this, I can take your normal force, using your friction equation, and multiply it by the coefficient of friction is 0.5. So 0.5 times 11 is just 5.5 newtons. Okay? So you have 5.5 going that way, you have 33.2 going to the right. So the net force winds up being this minus this, which gives you 27.7. And then to find acceleration, as we always do net force divided by mass. So 27.7 divided by 3 gives you a final answer of 9.2. Okay, pause the video if you need to write that down, because you're going to have to do two problems here that are very similar to that. Okay, so on your own, I want you to do the second half of 5. Since I did the first half of 5, it gets a little easy. It gets a little bit easier. All that changed here is the mass and the coefficient of friction. So again, this is the second half of 5 on page 8. Do that one on your own. Do this one on your own. And you are all done. And those are the last physics problems we are going to do. Okay? Did it have to work for you? Do the rest on your own. Hopefully I gave you enough information so you guys are able to work this on your own and solve some two-dimensional force problems. Good luck, and this will probably be my last video, so enjoy your long break. I will see you guys at January, and you'll start getting ready for semester exams with Mr. Lovett.